Okay, so the next part to this is we're looking at how do we actually go about measuring the change in enthalpy within a chemical system or any process really. Chemists use a type of apparatus called a calorimeter. Okay, so a calorimeter is essentially a piece of equipment that's used to measure energy change within a process, whether it's a chemical change or a physical change. But what you're doing is you're looking at the change in heat of the surroundings. Okay, so this goes back to that first lesson. So how the calorimeter works is the process or the system is happening within an aqueous environment. Okay, so typically water is part of the surroundings. So what happens here is we are trying to measure the change in energy. So we're measuring the change in energy of the surroundings by actually taking a measurement for the Q value, right? So determining the change in heat. By doing so, we can determine the change in enthalpy. So if you have an endothermic system, what happens is energy is absorbed from the surroundings, right? So the inside value would be a positive, but the value in terms of on the surroundings would be a negative. So our change in temperature would be a decrease, right? Be a negative value, and which means your Q would be a negative value and your delta H would be positive. So this goes back, please review that last lesson if this does not sound familiar. So an exothermic process means that you have a release of energy from the system. Where is that energy going? Into the surroundings. So your Q value is a positive, which means your delta T is in fact a positive. So you'd have a positive increase in temperature. Now, where this is happening, typically you need it to be, like I mentioned, you need water to be in the surroundings or some sort of aqueous solution. It doesn't have to necessarily be water. And then we need some sort of insulating material. Okay, so what we're trying to mimic here, of course, is a closed system. We want to try and minimize the amount of energy exchange. Actually, what we really want to try and mimic is an isolated system. We want the energy change from that thermometer to only be from the process that's happening inside of the calorimeter, which is why we try and keep this temperature isolated with an insulator, but it is impossible to ensure that that's happening. So you will always have some small amount of heat loss here, but that's actually one of the assumptions that we have to make when we're doing this. So a type of insulator that's actually great to use for calorimeters is Styrofoam. So here's an example of a calorimeter. So we have a Styrofoam cup, we have a thermometer, and of course we have a stir rod or something in here to ensure that the water is circulating. Okay, so polystyrene, that's essentially Styrofoam. Okay, so what we're doing there is, right, water is your surroundings, and the system would be the process that is happening inside of that water or within the water. And then by measuring the change in temperature, we can determine the heat change, which in fact would then give us the delta H value. Okay, so some assumptions that have to be made when you're using calorimeters, I did mention this before. So the first thing is you have to assume that there is no heat exchange between the calorimeter itself and the outside surrounding. So meaning the air or your hand, if it's touching the cup, or the cup itself, you're trying to assume that there is no energy being lost going in or out that way. So meaning this change in temperature that we are seeing on the thermometer, we are assuming that it is all coming from the system going on inside of the cup itself. Okay, the second assumption is that energy absorbed by the calorimeter itself is insignificant. So the Styrofoam cup itself, of course, will absorb some amount of heat, or release some heat depending on what type of process it is, but we assume that to be pretty much null and void. Okay, number 3 is an important one, especially when you're doing calculations with calorimeters. When you are dealing with an aqueous solution instead of water, okay, so let's say instead of water we had HCl, right, hydrochloric acid, AQ. You are to assume that even though this is hydrochloric acid, okay, since it is, the solvent is water in this case for the solution, the density and heat capacity is the same as water. So if you are trying to determine the change in mass or your C value for when you're determining your heat, if it is aqueous, no matter what type of solute is in there, you are to assume it is the same as water. And we're going to see that in this first example here. Okay, so let's take a look at a typical calorimeter example here. So we have a 100-gram sample of water. So we have mass of water, 100 grams, right? And it's placed in a coffee cup calorimeter. The solution temperature is measured at 14.4 degrees Celsius. Okay, so that's our initial temperature. Okay, and we have a 0.412 gram sample of calcium placed into the calorimeter. So the mass of calcium is 0.412 grams. And we're putting that into the calorimeter. So essentially what's happening is the calcium is reacting with the water, right? So we have a chemical reaction happening. When the reaction is complete, the temperature is recorded at, so we have final temperature at 24.6 degrees Celsius. Calculate the molar enthalpy for this reaction. So notice it's not asking for enthalpy change, it's asking for molar enthalpy change. So we have quite a few concepts that are kind of coming together here. So this reaction is involving both the system and the surroundings. Okay, so you have to think the water and these temperature changes that are being recorded are all from the surroundings. The actual system is the calcium reacting with water. This delta H is of the system. Remember, anytime you are referring to enthalpy, it is the system, whether it's molar enthalpy or regular enthalpy. So we have to have a way of combining all of the ideas that we've learned so far. So let's recap what we have. I'm doing it in a different color here. So we know Q is equal to MC delta T, right? We know that delta H, enthalpy, is equal to negative Q. And we know that delta H is equal to moles times delta H of the molar enthalpy, delta H R naught. Okay, so essentially, we have a situation where we have enough information to solve for Q. So remember that Q is for the surroundings. And the relationship between surroundings and system is inverse. So delta H, enthalpy, is equal to negative Q. So we know what Q is equal to. So if we were to sub this into our Q, we would get delta H is equal to negative MC delta T. All right, so we've kind of combined these two ideas, enthalpy and our surrounding heat. And then we have our delta HR is equal to moles times molar enthalpy. So if we were to sub this in to where our delta HR is, right, delta H of the reaction, we would have N times delta H naught is equal to negative Q again. Okay, so if we have a situation where we're trying to solve for molar enthalpy, we would just essentially want to isolate for delta H naught. So this formula that we've derived now, delta H naught of a reaction, is equal to negative Q, or negative MC delta T, over the number of moles. Okay, so this formula is going to come in handy if you are solving for the molar enthalpy for a system that happens to be within a calorimeter where you are measuring the surroundings. Okay, now keep in mind, you may not need this formula every single time. Maybe you're just trying to solve for enthalpy change. Maybe you're just trying to solve for the number of moles and you have other information here. This is just kind of combining the three different ideas that we've learned throughout these first two sections into one general equation. One thing to just keep in mind is all of the Q values. So this MC delta T are all in regard to the surroundings. The system is the moles along with the molar enthalpy. So if we were to continue this here, let's take a look at what we would be doing. Okay, so we have, let's use our combined formula, negative mc delta T over N. Okay, so our delta T, right, we have our T final and we have our T initial. So it's going to be it's always final minus the initial. So if we plug in those values here, we should get a change in temperature of 10.2 degrees Celsius. So just by seeing that this is a positive delta T, we know this is going to be an exothermic process, right? So our surroundings is gaining energy. That means the system had to be releasing it. The mass is the mass of water. So this mc delta T is all about the surroundings, which we made mention of. So the mass here is going to be 100 grams. The C is going to be the heat capacity of water, which is 4.18 joules per gram per degree Celsius. Okay. Mole value, the mole is for the system. So this is going to be our calcium that's being added into the water. So this is going to be mass over the molar mass of calcium, which is 0.412 grams over, we have a molar mass here of 40.08 grams per mole. Right, so our mole value for calcium is 0.0103 moles. Okay, so we essentially have everything. So the mass is going to be the mass of water. The C is the heat capacity of water. The delta T we calculated is the change in temperature of water. We're going to take the negative of that and divide it by the moles of calcium. So you should get a delta HR value being negative 413,941.75 joules per mole. Okay. And keep in mind, molar enthalpy is always in units of kilojoules per mole. So a reminder of doing that, you're going to divide that by 1,000. So if we do that by 1,000 and then we consider significant digits here. So just a reminder, temperature is not involved in significant digits. So when we're looking at this, you're looking at the 100.0 and the 0.412. So we have 3. So this ends up being a value of negative 414 kilojoules per mole. Okay, so essentially what that means is if you were to take 1 mole of calcium and react it with water, the system would release 414 kilojoules worth of energy, which would then in fact be absorbed by the surroundings. Okay, so for our next one here, it's a little bit simpler, okay, not quite as complex. If you pause the video and give this one a try, you have some information here, and you're told that this is happening with a dilute aqueous solution in a simple calorimeter. You have some data. Pause the video, give this a try, and let's see if we get to the same result. Okay, so we have here the mass of the solution. So this is our surroundings. We have the specific heat capacity of water. It's in an aqueous solution, and we have the initial final temperature. And notice here it's asking for the enthalpy change, not the molar enthalpy change. Okay, so really what you're doing here is Q is mc delta T. So those are all for the surroundings. And then to figure out the delta H, really it's just delta H is equal to negative Q. Okay, keeping in mind that it should be typically in the units of kilojoules. Okay, so just be mindful if it's asking for enthalpy or if it's asking for molar enthalpy.